Okay, thank you everyone for joining us once again. So it's another day for our meetup here in Abuja. So we are really, really appreciative of everyone that is joining us from all over the world. Thank you so much for your support, and we are really grateful. So today we're going to be looking at so we're going to be looking at nonlinear dynamical systems as chaos butterfly effect using R. Okay, I want to admit this person. So today we're going to be joined by our speaker, Abby. So he's going to be the one to take us through this topic. Now he's using R, how he's impacting himself knowledge-wise to use R. So we're going to listen to that. Before going, we're going to look at our agenda. So today we're welcoming all of you to the meetup, and we're really grateful you're here. So we're also going to go through introducing our organizers. So I'll also go ahead to introduce the speaker. So then we'll allow him to take us through what he's been using R to do. And it's going to be an amazing session for us. Then we'll take Q&A, maybe if he allows us during the time that he's speaking, or we'll wait for the time that we're going to be accepting questions. So the last thing will be to thank you all for joining us again. So I'm Bilikisu Olatunji. I'm the founder and co-organizer of the Abuja R User Group and R Ladies Abuja. So I'm also being supported by Stephen Fidelis, and we have a lot of people also as members who are also supporting us in the day-to-day activity, and also supporting us more by kind of motivating us to continue with all the services that we're giving here. So we're really appreciative of that. So I wouldn't take much of our time. Let me accept new people here, admit all. Okay, so I wouldn't take much of our time. We are all based here in Abuja, Nigeria, and we're really impacting ourselves with knowledge of R and advocating for the use of R here in Abuja in all sectors, professionally and also in the academics. So our sponsors are the R Consortium. We were really grateful for their support all these years. And we also have Business Data Laboratory Limited here in Abuja, which I am the principal consultant here. So we're really grateful for the support that we're getting from these organizations. So without taking much of our time, I'll put this into the screen. I would like to introduce our speaker. So our speaker today, as I would love to call him, Abhirup Moitra. Did I get that right?
Yes, you are right. You are keep trying. Good.
Okay, don't worry, I'll get to it. I think I'm comfortable with Abhi. So Abhi is a graduate of statistics. So he completed his graduation in statistics from Amity University in Kolkata. Okay, so Abhi also works as a scientific content creator in a learning platform named Cosmic Carrot. So he is also involved with an initiative taken by the fellows of the Indian Statistical Institute named Math Ganit. So his primary interest lies in mathematical statistics and theoretical statistics. So being a probability enthusiast, he employs dealing with challenging problems in the field of mathematics, mathematical statistics, and theoretical statistics, and making people realize how we can understand the pattern. So in today's talk, is going to be taking us on all this journey, how interesting it is to use R to find patterns in chaos. So I wouldn't want to go too much into that. I would want to hand over to Abby. So it's been a long waiting. I want to use this opportunity to really apologize that we had to reschedule. And we're really grateful that you're understanding and you've supported us all this while. And we're really grateful for that. I'm really grateful. So thank you so much, Abby. I'll allow you to share your screen now and take us through.
Yeah. Thank you, Bilikisu, for such a warm welcome, and thank you. So it's all right. So I'm not delaying. So without making you delay, so let me share my screen first. So yeah. So is my screen is sharing with you guys?
Not yet. We're not
Not
seeing
yet.
the screen.
Oh, okay,
Mhm.
okay, all right. Is it
Yeah, it's
visible?
coming up.
Okay.
Yeah.
Let me hide the bar. Okay, yes. So I guess it is visible to all of you. Yeah. Is it visible, Bilikisu?
Sure, it's visible
Okay.
or full screen. Yeah.
Yeah, okay. So let me first share that, make you understand that chaos, the term is basically enables us the qualities of the point at which the stability moves to instability or order moves to disorder. So for example, so this is very formal, but so I'll use sometimes for example and intuitions, or sometimes of the thought experiment to make you understand that what do you mean by this, because these things are very robust and very complicated. So actually, I have started to work on this when I was in semester 4. So it was 2021. So from that time, I just motivated by these things and these sort of things. Basically, so the chaos things encouraged me and motivate me when I was in 11th standard. So I was studying physics and all. So from that time, actually, I just encouraged by work and some visualizations. So I will say so. Yeah. So chaos is basically so for example, unlike the behavior of a pendulum, which adheres to a predictable pattern or chaotic system. So it does not settle into a predictable pattern due to its nonlinear processes. So chaos theory has been used to explain irregularities in lightning clouds, and so another scale, so stars and blood vessels. So it helps us to understand the turbulence found in all forms, so including fluids. Weather patterns are a perfect example of chaos theory. So weather patterns, basically, I'm saying. So this talk is a voyage into the extraordinary world of nonlinear systems and their dynamics. So I will try to deliver a coherent understanding of this, of the origins and the products of nonlinearity and chaos. So I'll say that intuitions and non-mathematical introductions lead you to explore a world of both extraordinary chaos, where some small event like a butterfly flapping its wings can be amplified into a tornado, but also a world of exceptional in the form of fractal similar structures that repeat themselves at various scales, one of nature's most ingenious tools for building itself. So, like quantum physics, the world of nonlinearity is inherently counterintuitive. So, it is a world where our basic assumptions start to break down and we get extraordinary results once the domain of obscure mathematics The concepts from nonlinear systems theory are increasingly proving relevant to the world of 21st century. So basically, what happened? So is my screen is not moving. Excuse me. Sorry, some glitches is happening. Excuse me, Billy Kisu. Hello.
Okay, hello. Yeah, I can hear you.
Yeah, I think my to all of you, right?
Yeah.
Okay. Thank you. So, okay, so consider so I'm starting again. So, okay. So consider the following situations. So you are a computer scientist. So assume you just assume that you are a computer scientist. So you are specializing in simulations of dynamical systems such as the weather surrounding your city or the trajectories of multiple planets affected by each other's gravitational pulls. So this is crucial, right? So this is crucial to your job. So you work for the weather forecast and also part-time in a intergalactic masterminds venture to attack and colonize the Milky Way. So now, as a result of extensive scientific research and your ingenuity, your simulations can perfectly predict how these systems change over time. So given any set of starting parameters. So however, you must still be extremely careful in using these simulations to predict what happens in the real world, or else it may result in a widely inaccurate. So completely different. So it is completely different prediction. So this is due to the simple fact that these systems are chaotic. So in mathematics, a dynamical systems basically systems in a that has a function that has described the time dependence of a point in a geometrical space. So examples of such are the mathematical models that describes the swinging of a clock pendulum, the number of fish each springtime in a lake, and the flow of water in a pipe. So at any given time, a dynamical system has a state given by tuple of real numbers. Okay, so you can visualize or understand, take it as a vector, so which can be represented by a point in an appropriate state space. So the evolution rule of the dynamical system is a function that describes what future states follow from the current state. Often the function is deterministic, that is, for a given time interval, only one future state follows from the current state. So moreover, some systems are stochastics, in that random events also affect the evolution of the state variables. So or you can define a dynamical system in such a way that like particle or ensemble of particles whose state variables over time and thus obeys differential equations. Okay, so I guess some sort of idea related with differential equations you are aware. So differential equations involving time derivatives. So to predict the system's future behavior and analytical solutions of such equations or their integration over time through computer simulations is made. So the study of dynamical systems is the focus of dynamical system theory, so which has applications in a wide variety of fields such as mathematics, physics, engineering, biology, chemistry, economics, medicines, and lots more. So there are a fundamental part of chaos theory. So logistic map dynamics and bifurcation theory, the self-assembly and self-organization process, and also the age of chaos concept. So So the objective of my talk is to deliver a coherent understanding of the origin and products of nonlinearity and chaos, and then we'll define, or the definition of a pattern in nature is a consistent form, design, or expression that is not random. The pattern can be found everywhere in nature. This is very important. So I'll explain these things also, and make people realize, so as I always do, so make people realize how we can understand the pattern in the chaos. So we'll cover all the key concepts from the domain, starting with the origins of how and why we get nonlinear phenomena. So I will talk about linearity versus nonlinearity, and the key concepts of the dynamical systems, the where does the chaos originate. So every topic, whenever you just studying any such particular topics or subjects, so there is always a motivations, or like where does these things originate, why these things exist, who invented or discovered this sort of thing, so like this. So where does the chaos originate? And fourth part is very, very important, that is Lorentz system. So this is the terminology which is quite relevant with chaos theory. So whatever is happened, chaos related things and stuff, basically the strange attractor or and stuff, so which is under comes under the Lorentz system. So we'll step by step we'll definitely discuss on these things, and there are lots of simulations, computer simulations, visualizations I prepared to understand these sort of things. Fifth is bifurcation theory, and we'll discuss about Feigenbaum diagram. So it is come under bifurcation theory. So we'll come into the brief introduction to attractor. So actually the definition of attractor, what is attractor, why we use attractor, and these things is very, very quite very mathematics related stuff, and I don't want to dive into the hardcore mathematics part. I just want to deliver a very basic understanding of mathematics or attractor, the concept of attractor. And the seventh and very important thing is Lorentz attractor. So Lorentz attractor is very, very important in our today's discussions, and most important thing is the chaos theory and butterfly effect. So we'll discuss about linearity versus non-linearity. So what do you mean by linearity? So linearity is a process of thought following known cycles or step-by-step progression, where a response to a step must be elicited before another step is taken. So I'll say that because of linearity, this is my own understanding I'm sharing with you guys. So there might be another opinions or things, so they can share after my talk. So what I believe that because of linearity is only one of the many behaviors of a function, equations, and system can have. So in general, linearity occurs if the if principle like superpositions and something like that, these sort of things basically can interpreted in many ways. So for example, I'll take a single variable function. So if you think about a single variable linear function, so it must be possible to think as a function of ax plus b. So this is very very easy function if you recall about the any linear functions. So however, if a function is non-linear, so there are infinitely many ways a function can be written as. So it can be a higher order polynomial, a sine, a hyperbolic cosine, the solution of a differential equations that cannot be expressed analytically. So, but it is surprising how much we can describe using linear approximations. So they are useful because they allow us to solve many problems that would be too complex otherwise. So even if reducing a problem to a linear one does not give us an ideally precise solution, it does help us to understand the behavior and mechanics of the equation and the problem being analyzed. So from here, it is come the definition that the non-linearity of a system defines that the change in the output is not proportional to the change in the output. So non-linearity is a term. So if you quite familiar with statistics, probability, and statistics, so you often heard about the independent variable or dependent variable and the linear relationship and something like that. So non-linearity is a term we used in statistics to probability and statistics, I should say. So to describe a situation where there is no linear relationship between an independent variable and a dependent variable. So philosophically or any intuitively, you can thought that human thought is characterized by expression in multiple directions rather than in one direction, and is based on the concept that there are multiple starting points from which one can apply logic to a problem. So it seems it is because linear thinking requires step-by-step deductions, and we have to start at a single step, since sometimes there are many more than one steps to start from the from non-linear thinking kicks in. So this is why we think in non-linear ways. So lots of things are linear within limits, I would say. So stretching springs, resistance, sound waves, light waves, but eventually even linear things run up against some constraint or limit. So you stretch a spring too far and it is not linear anymore. So you put too many volts across a resistor and it breaks down. So you mix enough loud sounds and the air pressure goes non-linear at 0 and gets hot and the high pressure points. So from here, we'll come to our key concept of dynamical systems. So the dynamical systems basically involve one or more variable that change over time according to autonomous differential equations. So autonomous, so as for example, you can say that dot x equals to, so you can say that x dot or dot x. So dot x is equals to minus y minus 0.1 x, and dot y equals to minus y minus 0.4 y. So it doesn't involve, so it only contains x and y variables, right? So this makes them autonomous, and each combination of x and y only corresponds to one combination dot x and y. So what do you mean by dot x here? So this is nothing but the rate of changes of x and x as time changes. So this is nothing but the dx dt part, and the dy dt, similarly the thing is the rate of change of y as time changes, right? And here comes that, where does the chaos originate? So as I have said that the butterfly effect. So the butterfly effect, if you ask that like why here the butterfly effect involved, so basically the butterfly effect is the idea that tiny causes like a flap of a butterfly wings in Brazil can have huge effects. So this is a metaphor which is quite related or related with chaos, the chaos theory and stuff. So So this is a completely metaphor. So now this idea comes straight from the title of a scientific paper, which is published nearly 50 year ago, and perhaps more than any other recent scientific concept. So it has captured the public imagination. So my goal is to answer those questions by examining the science behind the butterfly effect. So in the late 16s, after Isaac Newton had come up with his laws of motion and universal gravitation, everything seemed predictable. I mean, we could explain the motions of all the planets and moons, and we could predict an eclipse and the appearances of comets with pinpoint accuracy centuries in advance. So basically, so what happened, so this is basically, I will say that this is totally determinism, the view that the future is already fixed, so we just have to wait for it to manifest itself. So if you have studied a bit of physics, this is the natural viewpoint to come away with. So I mean, sure, there is a something called like, if you heard about Heisenberg principle and quantum mechanics stuff. So I mean, sure, there is the Heisenberg principle from quantum mechanics. So that's on the scale of atoms. So this is pretty insignificant on the scale of people. So virtually all the problems which I studied could be solved analytically, like the motion of planets, falling objects, or pendulums. So speaking of pendulums, so I want to look at a case of a simple pendulum to introduce an important representation of dynamical system, which is the phase space. So first, let me give you the clear the demonstrations of what do you mean by a simple pendulum. So a simple pendulum is a mechanical arrangement that demonstrate the periodic motion. So this is nonlinear systems. So this nonlinear systems is periodic. So it repeats itself over and over again at regular intervals. So meaning it means that it follows a repeating pattern. So if we start it twice from approximately the same point, we get approximately the same behavior. So visualizations I want to share with you guys. So let me clarify that is my screen is visible. So I have opened a new window. So is it visible to all of you? Just unmute yourself and please, anyone, please.
Yes, it's
okay.
We can say yes.
Yes. So I'm playing a visualization. So I guess this visualization is visible to you, right? Bilikiso, is it visible?
Actually, we can see the screen with simple pendulum and phase space, but I don't know.
So just
Is there any animation you're trying?
animated video I'm just sharing. So
No, it's not.
oh,
The
it is not,
animated video
it
is
is
not
not
sharing.
sharing. Okay. Let me share with you guys once. So okay. So okay, let me come to this. Actually, I'm unable to reshare my screen. So from
Okay, we can actually view. It's showing the animation now. Yeah, we can see the animation. I believe. Please kindly respond in the chat if you can see the animation.
Okay. Just I'm just saying that idea. Okay, so I'll share related relevant resources to for the audiences, those who are listening to me. So I'll say that some people is maybe familiar with the position time or velocity time graphs. So, but what if we wanted to make a 2D plot? So just try to visualize that if we wanted to make a 2D plot that represent every possible state of the pendulum. So every possible thing it could do in one graph will on the x-axis we can plot the angle of the pendulum, and y-axis it's the velocity, and this is what is called the phase space basically. So if the pendulum has friction, it will eventually slow down and stop, and this is shown in phase space by the inward spiral. Okay, so I'll just saying these things, just understand and try to get the insight. So I'll definitely share the related resources to help you understand. So if you have any questions from that, you can ask me after this session also. So I'm available in LinkedIn, and you can ask me mail. So yeah. So the pendulum when swings slower and less for each time, and it does not matter what the initial conditions are. Okay, so we know that the final state will be the pendulum at rest hanging straight down and from the graph. So it looks like the system in attracted to the origin. So that one is called the fixed point, the fixed point attract. Now, if the pendulum does not lose energy, okay, so well, it swings back and forth the same way each time, and in the phase space we get a loop. So the pendulum is going the fastest at the bottom, but the swing is in opposite directions as it goes back and forth. So and the closed loop tells us the motions in periodic and predictable anytime you see an image like any phase space. So you know the system is regularly repeats. So yeah, this is the my animations that I made myself. So this is the visualizations of double pendulums, and you can understand how this phase space is working. So I have written some code. So this code is basically dedicated to the beautiful chaos created by the double pendulums. So I have seen a great variety of animated versions that was pushing me to deal with such robust problems. So I'm not going to attempt to explain the math behind the double pendulum. So if you are interested, I will suggest some resources after this session. And so let me clarify this code and the things actually I just executed. So basically these are the parameters, or you can say these are the constants. Okay, so these are some constants. Okay, so you need to change to produce different pendulums. So you can just experiment yourself. So the code is here. So you can just take a screenshot or something like that. Or I will definitely share this sort of resources to you, so that you can play with these things and understand the insight of this work. So these are some constant that I have taken. So g is basically nothing but the acceleration due to gravity. So this is in the unit in meter per second square, and this is the L1, the first pendulum length. So you can see here. So this is the L1. This is the first pendulum. This is the mass of the first pendulum, that is denoted by M1, and this is the length of the second pendulum, and the M2 is the mass of the second pendulum attached with the first pendulum. So L1 or L2 is 1.0, and so M1 is 1.0, 1.0. I both have. I have taken. So the initial condition is very necessary, that is θ1 and θ2 I have mentioned over here. So these are the initial conditions. Okay, and the angular velocity of the pendulum. So this is the unit is degree per second, and here comes the
Please just
very
explain it now because you just say related learning in detection. That's all. They are not because when I check online, there are many in hospitals,
someone is
in schools,
asking
in
something.
workshop, in many places. And this one I should just start.
Excuse me. Okay, I
Sorry,
guess.
apologies for that. Sorry.
Okay. Fine. Okay, so basically, so I have written this, made these functions myself. So, so this chunk, this part of this chunk is basically the function of this entire system. So this is basically very important, and these things basically operate the whole the entire simulations. So I just made these things very basic level. So I'm not saying that I'm very quite pro in these things. So just I just played with these things and just made these things. So this is related to the mathematics part. So after I'll share the mathematics related stuff with these things to model this part. And this function which I developed myself is very much essential because this entire function will help you to execute the entire simulations. So now you need to now the partial derivatives needed can be calculated with the following functions. Okay, so this functions as this function needs to be integrated. So luckily there is the package called ODE int R. Okay, so this is the ODE int R package, and this make the things very easy. Okay, so the start, duration, and step size parameters basically control the time for your pendulum. And in the below example, I choose to swing the pendulum for 30 seconds. Okay, and the position is recalculated every 0.1 second. Right. And basically this plot will enable you to make this a double pendulum. So this part of chunks, this code chunks is basically help you to make this double pendulum, not this entire the path, the shadow path is showing. So this pendulum, this double pendulum attached, so this will just simulate it from this part. And second is very important. So if you just needed to compute the x and y coordinates for the pendulums from the angles theta obtained from the integrations, the final data frame, so this data frame is very important here. So basically this data frame, so this data frame is basically contains the exact positions of the pendulum for each time step. Okay, so animating the pendulums is straightforward with the package gg animate. So the things is so it will help you to build this sort of visualization. So actually this entire code is written in very basic understanding, the very basic mathematics governing with this the double pendulum idea. Okay, next we can also add also add some more details to the animation, like the tail of the second pendulum, the track its part. So it turned out to be a bit more tricky than expected though. So the trail needs to be added via a secondary data frame so that it can be animated with the transition time. So I used here the lag function here. So lag function to compute the trail from the last 5 time points. So also I use the shadow mark, so function to keep the past trail. So these things will allow to execute such a beautiful double pendulum. So that's it. So I won't go to the dig deep into the mathematics or the or very robust coding part. So you'll understand, I believe. So yeah. So you can play with the constants, initial conditions to create your own chaotic pendulums. So we
Abhirup, I have a
can
question.
sorry.
Abhirup, I have a question.
Yeah, you just you can ask questions after this session. Okay, so
Okay,
I'll
fine. Okay, fine.
request Bilikisu to take his questions. Okay, I'll jot down your all of these questions. So okay, I will answer one by one. Definitely. Just stay energized throughout the session. Yeah. So we can swing the pendulum with different amplitudes. So but the picture is in phase space is very similar, just a different sized loop. Now an important thing to note is that the curves never cross the phase space, and so you can see that the curves never cross the phase space. So as it is not cross the phase space, so that's because each point is uniquely identifies the completion of the system, and state and that state has only one future. So once you have defined the initial state, the entire future is determined. So this is what is called deterministic chaos, right? So deterministic, why deterministic? Because its future is determined by physical laws, although it seems random. Now, the mechanics of a pendulum can be well understood using Newtonian physics, but Newton himself was aware of problems that didn't submit to his equation so easily. So particularly the three-body problem. So calculating the motion of the Earth around the sun was simple enough, just with just those two bodies. But add in one more, say the moon, and it becomes virtually impossible. So Newton basically told his friend Edmund Halley so that the theory of the motions of the moon made him a headache and kept him awake so often that he could think it no more. So the problem as would become clear to Henry Poincar 200 years old later, and that was no simple solution to three-body problem. So Poincar had glimpsed what later became known as chaos. Okay. And here basically comes the idea of Lorentz research. So basically, I'll say that chaos came into focus in the 1960s when meteorologist Edward Lorentz to make a basic computer simulation of the Earth's atmosphere. So he had 12 equations and 12 variable things like temperature, pressure, humidity, and so on. And the computer would print out each time steps as a row and 12 numbers. So you could watch how they evolved, right? So now the breakthrough came when Lorentz wanted to redo a run, but as a shortcut. So he entered the numbers from halfway through a previous printout, and then he set the computer to calculate. After a while, when he saw the results, Lorentz was stunned. The new run followed the old one for a short while, but then it diverged, and pretty soon it was describing a different state of the atmosphere. I mean, different weather.
No, office.
So Lorentz first thought, of course, was that the computer had broken, maybe the vacuum tube had blown, but none had. So the real reason for the difference came down to the fact the printer rounded to 3 decimal places, whereas the computer calculated with 6. So when he entered those initial conditions, the difference of less than 1 part in the 1000 created different weather just a short time into the future. So now Lorentz tried simplifying his equation and then simplifying them some more down to just 3 equations and 3 variables that represent that toy model of convection. And essentially the a 2D slice of the atmosphere heated at the bottom and cooled at the top. But again, he got the same type of behavior. If he changed the number just a tiny bit, result diverged dramatically. So Lorentz systems is basically displayed what's become known as the sensitive dependencies on initial time conditions. So basically Lorentz was trying to, as I said, that Lorentz tried simplifying his equations and then simplifying them some more down to just 3 equations and 3 variables that represent the toy model convection. So you can see the 3 equations, that is these 3 ordinary differential equations with the initial conditions x, y, and z0 is 1. So the constants sigma, rho, and beta are system parameters. Okay, systems parameters, which is proportional to the Prandtl number or Rayleigh number. And you can explore what is Rayleigh number and this Prandtl number here. Okay, so this is very important, and the certain physical dimensions of the layer itself, where the sigma, rho, and beta are 3 parameters with values of sigma 10, beta 8/3, and rho 28. So implementation of an intermediate value initial value problem in ODE in ARC can be separated into 2 parts. So I just separated these things into 2 parts, that is the model specification and the model application. So model specification consists the defining model parameters and their values, defining model state variables and their initial conditions, and implementing the model equations that calculate the rate of change, that is the dx/dt part, as I mentioned previous slides, on the state variable. And here comes the model specifications consist of, so specification of the time at which the model output is wanted, so and the integration of the model equation. So I use the R package, the dsolve package. So I will come to the dsolve package later. So if you have any queries or if you want the resources, relevant resources dsolve, so I will definitely mention after this session. So, and here comes the plotting of model results. Okay, so model specifications, there are 3 model parameters, that is the S, R, and B. So what does this S? So S is nothing, just the sigma. Okay, the sigma 10. So here it is S10, the sigma 10. R is 28, that is the rho 28, and the B means the beta 8/3, right? And the state variables, the 3 state variables are also created as a vector, and their initial values are given. So okay, and here comes next comes the model equation. The model equations are specified in a function that calculates the rate of changes of the state variables. Okay, so input to the function is the model time, so and the value of the state variables and the parameters in that order. So this function will be called the R routine, and that solves the differential equations. So the code is most readable if we can address the parameters and the state variables by their names. So as both parameters and state variables are vectors, so they are converted into a list. Okay, and the statement which as dot list, okay, the as dot list, and then under concatenate the state and parameters is defined. So then it makes the available the names of the list. So the main part of the model calculates the rate of change of the state variable, and the end of the function, these rates of change are returned packed as a list. So note that it is necessary. Okay, so remember that it is necessary to return the rate of change in the same ordering as the specification of the state variable. So this is very important. So in this case, as state variables are specified, x first and then y and then z, the rates of the changes are returned as dx, dy and dz. So here it is the dx, dy and dz. So basically this is the so main three equations as I mentioned over here. And then come the model application. So then, so under model application, it comes the time specification. So we run the model for 100 days and give output at 0.01 daily intervals. So our functions, that is sequence, create the time sequences. So you can say see that this is this create the time sequences, and then it is come the model integration. So the model is solved using dsolves function, that is that enables to execute the ODE, the ordinary differential equation, so which is the default integration routine. So function ODE takes as input the state variable vector y, the time at which the output is required, the model function that return the rate of change, and the parameter vectors, that is params. So the function ODE returns an object of class dsolve with a matrix that contains the values of the state variables at the requested output times. And finally, the model output is plotted. So I use the plot method designed for object class dsolve, which will neatly arrange the figures into 2 rows and 2 columns before plotting the size of the outer upper margin. So the third so we can access to XYZ respectively univariate time series. So as the time interval used to numerically integrate the differential equations was rather tiny, so we just use every 10th observations. Okay, and essentially a 2D slice of the atmosphere heated at the bottom and the cooled at the top. But again, Lorentz got same type of behavior. He changed the number, the number of what should I say? The same type of behavior if they change the number just a tiny bit. Okay, so the results basically dramatically diverge. So Lorentz system basically displayed what's become known as the sensitive dependencies on the initial time conditions, which is the hallmark of chaos. Remember, so which is the so now since Lorentz was working with 3 variables, we can plot the phase space of this system in the 3 dimensions. So we can pick any points as our initial state and watch how it evolves. So this is basically 2D a diagram. So here you can understand that how these things basically evolve. Okay. Here it is come the bifurcation theory. So starting from the Poincare research on the instabilities of the celestial bodies, celestial trajectories at the end of the 19th century. So chaos has the emerged as an important field of study for most of the natural sciences. So the catalytic paper in the development of the field was written by Paul Lorentz more than 50 years ago. So his research involved weather forecasting with statistical analysis of weather data. So he experimented with various systems of differential equations, and he made a simple yet crucial observations that the evolution of a system is very sensitive with its initial conditions. So he presented a system of three coupled differential equations model, the fluid dynamics of the weather within a simplistic framework. So plotting the trajectories of the system for particular initial conditions reveal not only the sensitivity of the system, but also that there was an attractive region that within the system was bounded to evil. Okay, and yet was more to come a few years later. I guess you are quite aware with this company named Hewlett Packard. So Hewlett Packard basically released the programmable pocket calculator, that is HP 65. That is a cutting edge technology for its time. So it was the first programmable handheld calculator in outer space, but also it was one of the first pocket programmable device that witnessed chaos. So Mitchell Feigenbaum or Feigenbaum, whatever you can pronounce. So he started calculating the cosine function iteratively, and initial angle of HP 65 after some iterations always return to the point something the approximately the 0.739. So of course this discussion went much further, and HP 65 could do much more complicated task that opened the discussion to the notion of universality in chaos. So, but let us remain at this crucial point and do experiment, some experimentations our own language programming environment. So I'll use here is apply function. So previously, so first going to describe about my coding part. So let me clarify what does asapply do. So asapply function starts an iterations along the values we provide in the first argument. A new environment is created in each step for the function we define. So if we don't send the calculated value to the parent environment, it will be lost. It will be lost when the new environment will be invoked in the next step. So what I just did was calculate the sequence of x n plus 1 equals to cos xn for 100 steps. Okay, so be cautious of the double arrow assignment. Okay, because the environments of the functions calls are done in each step of the asapply. So do not communicate, but they are all children of the parent frame. So within their scope, so we can do this this also with a classic and simple for loop, but when you go the asapply, so way it is fun and pays off when more complicated operations are involved. So the latter relation belongs to the family of one-dimensional maps, and we have described its behavior as a damped oscillations that converges to the stable value 0.739. So these values is solution to the transcendental equations, that is x equal to cos x. So so I guess this this plot, this visualizations will make this more clear. So plotting it is straightforward to see the once the iteration reaches 0.739, so it's stabilized to a Bezier value. So let's spice things up, okay, and add a free parameter. So we have an angle, so let's try to a parameter name, namely the xn plus 1, that is r cos xn. So if we calculate a range of r parameter within its range, close range, that is 1.5 to 2.9, and see how the system behaves, okay. And in particular, we will we calculated a sequence for 9 distinct value of r. So to identify this state transition, we can plot the Feigenbaum diagram, and that's how it is look like. So to get this diagram, we'll let the system evolve for a considerable amount of iterations and collect the tail of the sequence that we generated. So this process is basically repeated for a range of r. So this is one of the best visualizations to communicate with the concept of bifurcation theory. So often it is called the bifurcation diagram. So the formal name, I will say that this is Feigenbaum diagram or the Feigenbaum diagram, whatever you can say. And here it is come and the brief introduction to our attractors. So before, whenever you will try to understand what do you mean by attractor, so you have to come through some specific terminology, which is called the phase space and state space. So this is basically a Cartesian space. So I guess you are quite aware with the Cartesian space. So this is basically concept of 7th or 8th standard concept, mathematics concept. So this is a Cartesian space where the axes are the system's variable. So each point in the space is unique state of the system and has its rate of change, which can be shown as a vector. So for each specific system shown, the vector fields, so this is the vector field. So this this is how this entire vectors field look like. So if you try to imagine, you are trying to scatter a bunch of random points around to represent different possible states, and you will see how they evolve and move around. So it seems like they all spiral toward the center. So you can see this. So it is spiral toward the center. So this brings us to our next topic. So here the attractor is just the origin, and the basin of attractions is very every point in the space. So an attractor is basically nothing but a set of point in the phase space which attracts. So you have understood this phase space, and so the attractor is basically a set of points in the phase space which attracts all the trajectories in a certain area surrounding it, known at the basin of attraction. Okay, so that is what I just mentioned, the basin of attraction. So for example, so if you just notice the previous example I just said, that dot x, the dot x equals to the same equation, the minus y minus 0.1x, and the dot y equals to y minus 0.4y. So notice that the origin where the x equals to 0 and y equals to 0, the dot x and dot y is 0, 2. Okay. And here comes our some two more famous attractor. So one of the most prominent strange attractors based on a quadratic map is the so-called Hainaut map. So not Hainan, so this is Hainaut map. I guess it is Hainaut. The pronunciation is Hainaut because this is the French pronunciation, and I can't pronounce French. Okay, so so maybe whoever is quite aware with French, so maybe maybe I am wrong, Hainaut map. But the idea is basically important. So named after the French mathematician Michael Henao. So the Henao map is typically written as this mathematical format. So with the parameter or the, you can say, the coefficient term is 0.9, A is 0.9 and B is 0.3 respectively. Another well-known chaotic quadratic map is Tinkerable map, so which is commonly known as using this model. Okay, so here so what I just did here, so you can see these visualizations here, so I can zoom. So if you able to visualize this, so yeah, so it is basically programmed in our own program environment, so our program environment. So plot, so as we program different coloring options into our plot function. Okay, so this is called hypnotic images. Okay, so it is programmed different coloring options into our plot function, so we can even produce plots with different colors. Okay, and here it is comes our own some strange attractors. So how did I executed it? Yeah, I wrote some code, and every time I just run those code, I got a whole new set of strange attractors. So some might be look little boring, but if you will produce, maybe they look much better than mine. Okay, so these patterns are quite fascinating, I believe. So here it is comes the Lorentz attractor. So if we specify Lorentz equations and plot in 3 dimensions on a modern computer, the location of the first point is arbitrary. So let me see, it is possible to share my screen again for to write some R codes to make this more interactive. So let me just escape. Yeah, and let me share my screen again. So is my R script is visible to all of you?
Yes.
Yes.
Okay, thank you. So so as I said, that if we specify Lorentz equations and plot the 3 dimensions on a modern computer, so the location of the first point is arbitrary. Okay, with each point after that, the computer steps forward in the time by calculating the positions of the next point based on the position of the previous one. So it seems to change the directions at random, and it never arrives at the same point twice. So this is the R library I just used. So this is the dsolve package for solving the differential equations, and for interactive 3D plots, this is Plotly. So this is amazing. So I'm just specifying the equations here. Okay, so let me run. Yeah. So if it did that would be the so as I said, so if we did something like that, so it that would be the beginning of repeating pattern. So this type of system is known as a strange attractor. Okay, so and this particularly known as the Lorentz attractor. So let's solve the system of equations numerically first. So there is a number of packages that can numerically solve the differential equations in R. So as I said, so one of them is dsolve, which is one I'm using here, and I don't know enough math to solve the equations analytically. Okay, so I resort to a numeric solution. So what I mean by numeric is that the time is discretized. So here into step of 0.01, Okay, so 0.01. So as you see, 0.01 time unit. So since we know from the equation themselves how x, y, and z changes through the time, so we can use a variety of methods to compute what the values of x, y, z in the text in the next time step. So will be their values at present. So starting from the initial conditions when time is 0. So I used ODE 45 method. So it is a numerical computational method. So which is basically in formally it is known as the Runge-Kutta method. So this is one of the finest numerical computation solving method. So specifying the parameters. So as I mentioned, that is sigma, beta, and rho. So the parameters are specified, and the initial conditions. So you can change the initial conditions according to your preference. So this is not hard and fast that the initial condition has to be this and so. And here comes the time over which the equations are numerically solved in 100 units. So we'll solve so you can see this solve. This solve is basically nothing but the data frame, okay, that contains a numerical solution. And so let me run this code. Yeah, and now we want to plot the approximation solution. So plotting in Plotly is quite is like the interactive. It is quite interactive, and you'll see why it is interactive. So let me run this first. And basically it is the interactive version of completely interactive version. So you can see that this x equals to tilde x, nothing but you can compare with ggplot2's aesthetic. Okay, so x tilde x and y tilde y and z tilde z. So yeah, so let me zoom this. So let me zoom this. Yeah, I guess it is visible to all of you. Is it visible, Bilikisu?
Yes.
Yes,
This visualization,
yes,
the
yes.
interactive visualizations, yes.
Yes,
So
maybe you can
this is-
open the window. Can you open the window a little more, the pane? So
okay,
that we can see.
the presentation.
Just shift,
Okay.
yeah, no, just shift the, no,
Okay.
kind of the, yeah,
Yeah, okay. Thank you. Yeah.
okay.
So you can see this is how I just made it. So let me fix it. Okay. Yeah, so this is the iconic butterfly. So we also see how the state of the systems transverse between two wings of the butterfly through time. So basically trajectories are just curves. Why? So it is a poster child of chaos theory, and is sometimes almost synonymous with the butterfly effect or the field of chaos theory itself. So it even looks like a butterfly. Okay, a strange attractor is one that has a fractal structure. So I'm not going to describe the fractal structure. What do you mean by fractal? So this is completely different terminology and a completely different study. So I don't know much about fractals. So I'm keep studying on it. So so now point in space is very visited more than once by the same trajectory. So you can see from here and see these visualizations again. So I'll say that no point in space is ever visited more than once by the same trajectory. If that happened, the trajectory would travel in a predictable loop, and no two trajectories will never intersect. So if that happened, they would merge into the same path. So giving two different sets of initial conditions, the same outcome is that a single trajectory will visit an infinite number of points in this limited space. So and this limited space will have an infinite number of trajectories. So this is the reason that this attractor is said to have non-integer dimensions. So it is made up of infinitely long curves in a finite space, which are so detailed that they start to partially fill up a higher dimension. So let me clarify and the things that it is not one-dimensional, not two-dimensional, or not three-dimensional. So it is dimension. So its dimension is somewhere in between. So as a result of this non-integer dimension and detail of arbitrarily small scales, the set of points in Lorentz attractor is a fractal space. Okay, so that's why I'm saying this is so these entire visualizations just make it more visible to all of you, and so that's why it is in I'm just programmed in very so-called the Cartesian plane and the Cartesian coordinates. So but this is not the case. So and that's why it is called strange, as it is not follow the one dimension or two dimension or three dimension. So yeah, so the whole idea that certain systems have these finite predictions horizons that you can go beyond, which was really new. So nobody imagined that to be the case. So when Lorentz presented his work at a conference in 1972, the organizer didn't receive this talk, the title in time. So he suggested one. So does the flap of a butterfly's wings in Brazil sets off a tornado in Texas? So the butterfly instead of seagull became the image most associated with his work. And this is so with so it has it had increasingly profound impact on a number of disciplines. In its first 10 years, Lorentz 1963 paper was cited in about 10 other publications. So since then it's been cited over 9,000 times in the paper from nearly every field of science. So in 1987, a popular book by James Gleick introduced the world of the work. So I can show you this book. So I guess it is visible in my camera. So if you just see my main camera, so I guess this book is visible to all of you, and if it is not, so I guess the PPT is enough to understand. So the book is quite wonderful. But I haven't completed entire book. So but the motivations of my work and the chaos related stuffs and whatever I have just received from this book. So it is very important, those who are working such things. So I would suggest them please go through these books. So it is a bestseller on that time. And so coming back to the topic, so the book is the world to the work of Lorentz and the other chaos pioneers. So and the butterfly effect became the most popular culture on that time. Like
I know.
since
Both
Albert
inside and
Einstein's
inside.
work, you know, the special theory of relativity and stuff, and whatever he worked, and that's how he famous in scientific communities. And So that's how this chaos and butterfly effect and his work famous and make him more popular. So the butterfly effect is a theory according to which the smallest things such as a butterfly flapping its wings can create a series of events leading to a catastrophe such as a tornado. So scientists continue to create mathematical models of more nonlinear systems. So if those models are correct, deterministic chaos can be found in some fascinating places, including financial markets, okay, as well as the eye movements of people with the certain brain disorders, okay, in the onset of sickle cell disease in the human body, and in the fluctuations of human and animal populations. Okay, so the world is, as I said, that the pattern in chaos, and I previously said in my things that the beautiful pattern is everywhere. So the world is full of natural visual patterns, from the spots on a leopard to spirals of the fiddle head fern. So some patterns are as small as the molecular arrangement of the crystals and as big as the massive spiral pattern of the Milky Way galaxy. So patterns can be found everywhere in nature. So while one might think of patterns as uniform, regular, so some patterns appear more random yet consistent. And the definition of a pattern in nature is a consistent form, design, or expressions that is not random. So if people have heard anything about the butterfly effect, it is usually about how tiny causes, I'm again saying that how tiny causes make the future unpredictable. But the science behind butterfly effect also reveals a deep and beautiful structure underlying the dynamics. So one that can provide useful insight into the behavior of a system. So you can't predict how any individual state will evolve, but you can say how a collection of states evolves, and at least in that case of Lorentz equations, so they take the shape of butterfly. So yeah, we are
Okay.
in. So
Okay.
I'll say that my aim was to share fundamental and frontier ideas and techniques for modern science and technology that can stimulate research interest in the exploration of mathematical applications and directly pass the new knowledge to the next generations. And I hope I have achieved my objective through this talk and session. So thank you audience for your patience, and I'm thankful to the entire R Abuja group and Bilikisu. Thank you for listening to my talk. Yeah, so I'm handing over this platform to Bilikisu again.
Oh, well, that was really a wonderful presentation. Thank you so much. Although we have people who have questions here, I hope they're still around. So so if you have any questions or question, you want to unmute yourself, you can go ahead now.
Let me just let me just do the full screen here.
Okay. Okay, so you can go ahead and ask your
this
question.
Okay.
Okay, there's a question
I'm just
here.
taking questions. Just let me give some time. Actually, I'm unable to. Actually, how should I unshare my screen? Can you tell me?
Okay, maybe I should. Yeah. Okay. Let me go.
Okay. Let me ask let them ask the questions, and I'll try my best to get the answer.
Okay.
So someone is asking question in between my talk. So please ask him.
Okay. So let me go ahead and read the ones in the chat. So can there there's something by Indrajit. So he's asking, can there exist n function theory for any n greater than 2? What is graphical representation? So he also asks, what is the uses of all alpha 1, 2, 3? Actually, I'm not familiar with this theory.
Yeah,
I think you
actually what he's
maybe
saying,
you
actually I'm not
understand.
able to see the comment section. So let me first see the comment. Actually, there is some problem is occurring in my side. So just okay, not.
So can you read the question in the chat?
No. Actually, I'm not unable to read the questions. Actually, what is happening? I'm not getting that. What is the where is
Okay,
the
let's
chat
go.
box? I'm
Okay,
unable
can I
to.
go over it again? Sorry, just
Okay,
hold
okay.
on.
Again, can you just say the questions again?
Okay, I'm coming now. So just to double check if I have other questions there. Okay, he's asking, how can we graphically represent if there have any finite or theoretically infinite number of pendulum? Do you understand that?
Not see. Theoretically infinite number of pendulums. Okay, I'm not getting so, but still I'm trying to answer this question. So I guess he's asking that if it is possible to design some more things, more complicated visualizations or complicated pendulums. Like I have attached double, so can we attach four more pendulums in it? So I guess this is what he asking. So it is possible. Okay, definitely it is possible. So or we can simulate, we can just see the visualizations and chaotic patterns, and obviously we can set some readings to get these things. And if we so if we just get these readings, and we can work in like build some mathematical models related with chaos, like or model something. Like it depends on studies, that what you studies you are going to encounter. Okay, so so it is not something like if I design something pendulum, so you your motivations or your what you are trying to execute, that has to be very clarified. It is possible that if you just put two pendulum here, again one more, and then you can play with this graph. So why you are trying to playing this graph? So basically what I have designed. Okay, so this is the showcase or portray the idea of chaos, the deterministic chaos, the double pendulum. So idea basically popped up from there. Okay, so it is possible you can attach more pendulums, make it more complicated, and just do some. Yeah, the screen is here, so yeah, I can see the things. Yes. So yes. So yes, this chat section is visible too for me. Yeah. Someone is asking, yeah, can there exist in function key? What is infurcations? Infurcations, I'm not clear with infurcations or in functions or in something. What is graphically represent? What is it graphical representation? What is the use of
Okay, I think
alpha 1
sorry,
to 3? Where is
sorry,
what
I think
where
sorry.
he is
Hello,
seeing the alpha and stuff?
hello.
I'm not getting. Yes.
Okay, sorry, just hold on. Okay, I think Indrajit is still here. So would you
Okay.
want to ask your question yourself?
Yes, he can ask his questions himself. So I'll clarify these things more.
Can you
He
hear
can,
me, Indrajit?
yes. Like bifurcation. Like bifurcation. What like bifurcation? I mean, be specific with your question.
Okay,
I will say, like, just take your time. Just be specific with your question. Okay. So if
okay,
there is
sorry.
more
I
question.
think he said in hello. Can you just hold on? He's saying that like bifurcation or something. Look at the charts. So it's
Yes,
trying to.
I'm just getting. So he's asking that can there exist a okay? Can there exist okay? Can there exist bifurcation theory for any n greater than 2? What is it? Graphical represent? Yeah. Okay. Now I got his questions. Okay. Yeah, it is possible. And what is it? Graphical representations. Okay. See, the bifurcation diagram or whatever I just shown in my presentations, or the Feigenbaum diagram, that is more related. So yeah, it is possible. Okay, so I don't think that would change the same pattern. So this is repeatedly happening. Okay, so as it is repeatedly process the same steps, okay, same diagram. So whatever may be your initial, so whatever may the your the initial entries or initial conditions, it doesn't matter. So from where you are starting, it doesn't matter, or whatever you just said, the parameters I have mentioned over are in 1.5 to 2.9 in close range. Okay, it doesn't matter. So you can change, you can just do the thing according to your preference, but the output, the visualizations will be similar with these things. Maybe the values can be changed, okay, as you are changing the initial values. So it is possible. Okay, I think I'm clear with my answer. Maybe if it is, if he has more doubt, he can ask questions. He can mail me. You can WhatsApp me, whatever. So, is there any more questions?
Okay, I think this is the last question. So if I think we don't have no more questions here.
Oh,
So
how
I
can
think this.
okay? Someone is okay. Someone is
No, it's still the same thing, I think. So it's still
how
intricate.
can we graphically represent it if there have any finite theoretical infinity number of pendulum? Yeah, I just said infinite
So,
number of pendulum. So can you, I will ask same thing to him. So can you know the value of infinity? So if you want to put the infinite number of pendulums, hey, you can just intuitively understand the infinite number of pendulums, like the very large number of pendulums, like 1,000 pendulum, 2,000, 7,000, crore, lakhs. Okay, we can play. Okay, so
okay.
yeah, so
Okay.
you need motivation. So why you are putting so many pendulums, and what is the purpose of your study? Yeah, it is possible if you have time, if you have patience to experiment with those 7,000 pendulums and stuff. You
Okay.
can find the beautiful patterns, but yeah, one more new message.
Okay.
I mean the sequential function of functions of pendulums. Yeah, it is possible. It is possible. Definitely you can study, you can explore with your ideas. Yeah, you are basically
Okay, I think
yes.
okay. Yeah. I think this will be the last question we're going to take for today. So because we're running out of time here, it's late. So I think this would be the last question, and I don't think there's no question in the chat again. So I want to use this opportunity to really appreciate all those who have stayed with us to the end of this program. Yeah, we know it's a tough topic to discuss today. So, but we believe that you can still connect with us on LinkedIn, and we'll connect you with Abby. So he will be able to answer most of your questions, and I believe he's always available. So there's a lot you can do
I
with
will
R.
definitely provide all the resources, okay, related
Okay.
to this.
Okay.
In
So
the
there's a lot we can do with R. And I believe we're all explorers. We're all very, very inquisitive. We can explore a lot of areas in science, in academics, social sciences, name it, marketing, there's a lot you can do with R. So it's not limited to just the statisticians, but there are a lot of things you can do, and just try and give R a shot. And I believe you can do so much. So at this point, I want to say a big thank you to Abby and to everyone that has joined us from all
I'm
over
really,
the world,
really honored
and
to be part of it.
especially, yeah, thank you. So, and especially a big thanks to our members who are also available to join us. So we want to appreciate the R Consortium for their sponsorship, and we also appreciate Business Data Laboratory and everyone that has been supporting us morally. We are really grateful. So at this point, I would like to say goodbye, and we look forward to meeting you next time. So thank you so much.
I'm leaving.